Good afternoon, everyone. So I think we can start. So I am Luc Bourlier. I'm from Lightband. I think from right now you should all know who we are and what we are for more type safe. If we still don't know, we have a booth in the exposition hall, so just come see us. And today I will speak about connecting reactive application and fast data. So the title is a bit buzzwordy, so I will go through the different ideas of the title first to make sure that we understand what we speak about, and then describe what can be the problems of connecting big data, fast data with reactive applications, and see how we can solve the problem. Okay. Oh, second slide of intro. So reactive applications. Who still don't know what is a reactive manifesto and reactive applications? Okay. So just go reverse back on the thing. Reactive manifesto is a description of what we think that reactive application should be. So being elastic, responsive, resilient, and message-driven. So you can be resilient to any kind of problem. Kind of situations, resilient to the volume of data you receive, resilient to any failure, and be able to respond to send response in a timely manner, even if your system is decoded. So that's reactive applications. So fast data. I'm pretty sure that people are less knowledgeable of fast data at this conference. So let's start back from big data. Big data, the big data movement started sometime in the middle of the 2000s when the big internet companies started to have too much data to be able to manage them with the traditional tools. So when we speak about big data, when your data doesn't fit in one machine, so it's one characteristic, or it doesn't work well in a classical database, even if they are working on multiple machines. The way it was solved, so the basic ideas were published by Google in two different papers, one describing a way to create a distributed file system which is resilient and redundant, working on cheap hardware, community hardware, and MapReduce, which is a way to execute operation on this type of distributed file system. So fast data, the idea of fast data, basically you go forward about 10 years, and people want to apply the same ideas as big data, but instead of using your data that you have somewhere stored in big cluster, you want to do the same kind of operation on data which is incoming directly from your web services or any application you have. And with the idea that to get a really fast update of what's happening in your system. So one logical way that thing goes in the company is you're lucky enough that your managers tell you, go ahead, you can do some big data. So you have access to all the data that your company aggregated over time, and you start to do analysis on it, and you get some interesting information about, I don't know, why how often does some service is going down or things like that, some interesting information. And your manager says, great, but that's historical data. Can we get data about what's happening now? And you start to run your analysis every day. And every day, every morning, you can check that what happened the day before, and it's nice, but your manager always wants more. And manager says, well, can we just short a bit the cycle? Because if we know really fast that something is going wrong, we can fix it. So we start to get early, and when you move from historical data to daily, usually you can do it fairly well. You can still run during the day whatever data you received the day before. It's fine. When you go to early updates, usually you need more than just the 1 hour of data. You need data from the last 24 hours to be able to get some good analysis. And it starts to get tricky to process the data from 24 hours in 1 hour. It might be starting to get tricky. So you may start to switch a bit the way you do it. And after a while, your manager tells you, we want to know as soon as possible when there's any problem. And then you get to fast data, when you need to have a streaming engine to process your data and to surface any problem or any specific things that are changing that you need to know. So that's how, in a lot of cases, we get from big data to fast data. So us at Lightbend, and almost everybody with doing reactive applications and thinking about big data are working with Spark and Spark streaming. A few reasons for that. One which is not to pass by is Spark is written in Scala. And the way you program Spark, it looks a lot like the way you program the Scala collection. You do the maps, you have the same map, same flat map, same group by. The semantic behind it might be slightly different, but the way you write your code is exactly the same as if you do work on Scala collection. So it's really simple to pick up for Scala developers. So the big grandparent of big data is Hadoop, which is implementing the basic MapReduce model. The MapReduce model works really well, but after some time, it really shows some problems, or some limitations, more than problems. And the limitations are mostly that it's not really good at doing iterative algorithm. And nowadays, the big thing is machine learning algorithm, and machine learning algorithm are all based about iteration over and over on the same data to reduce the volume of data to some information which is usable. So Spark is really good to do that, and also so after having solving some of the reasons why Hadoop was not really good at iterative computation, they went a step further, and now when you do a Spark, when you create a Spark job, when you code your Spark application, what you describe is a graph of operation to execute over some data. And Spark takes your graph and recompile it in such a way that it runs very fast. So in the last version of Spark, they did a big amount of work to take your model of execution, or the model of what you want to do, algorithm you want to do on your application, on your data, and to compile it and optimize it in such a way that it runs really well on the clusters. So yeah, so that's it won't be really useful much, but it's a description of the basic way of a Spark application works. So you have a cluster manager, which is something that just manages a cluster and allow you to, you can ask the cluster manager, I have a job, I want, I don't know, 64 cores and 20 gig of memory to run my Spark job. And the cluster manager will give you these resources. And after that, the driver program, which is really your application, will send directly to the executor, to the nodes on your cluster, the work to be executed, which will be executed on the data which is in your cluster, and you can get the data back on your driver or push it in next data store for further analysis or things like that. So Spark is great, and Spark is so great that they thought that we could also use the model of Spark not only for big batch job, but to do it also on streaming. And the way they went about it is to go with the idea of mini batching. So the idea of mini batching is to run the same type of operation that you do in Spark normal, but on really small amount of data. And what is mini batch is whatever data you received in a set interval. So you define your Spark job to say, I want to run every, whatever, 1 second, 5 seconds, let's say 5 seconds. And during 5 seconds, Spark will receive data coming from your application, some stream of data somewhere, store it locally, keep it, make it resilient and everything needed. And at the end of the 5 seconds, it will start a job which will compute some analysis over the data you receive in the 5 seconds. The great thing with Spark streaming is you can basically you created code to run on the data you had stored statically somewhere. You can run exactly the same code on the streaming data. So that's a very good thing. And to be even more powerful, there is additional operations which are specific to streaming, because so as I said, you execute a normal big data job on some really small set of data, which might not be enough data to be relevant. So you can say to Spark Streaming to, in fact, every 5 seconds, run my computation over the last 5 minutes. and things like that. And you can also keep state over time to do stupid things like, well, simple things, like counting the number of requests for different URL you get and things like that. So you can just do all those kind of things. So yes, that's what I explained. At each interval, you get the data, and then you run a Spark computation on the data. Reactive application is mostly about resilient to all kinds of things, and without directly working on the Reactive manifesto, Spark and Spark Streaming implement most of what's in the Reactive manifesto. So it has support to recover for all kind of failures. So looking specifically at Spark Streaming and fast data, it recovers without problem if your full application dies or something like that. It recovers and will reprocess and connect back to the producer of data and asking if you use the right producer of data, ask it to please restart at a specific point where I was stopped and continue to process the data from that. And there is also some support to manage excess volume of data. So that's what I will mostly show you as a big problem, as a potential big problems, because it's when you need coordination between systems. Everything else Spark managed by itself. If you're on Spark on some cluster manager, one node dies, the cluster manager can automatically restart another node, and if some data has been lost, it can be recreated or recovered from some checkpoints. So most of everything is managed by Spark itself internally, but if you speak about high volume of data, then you need to have some more synchronization with outside world. So it's what we will see. Yeah, so just to show you, we'll go for a demo, and to do the demo, I will use my little small Raspberry Pi cluster. So why do I use my Pi cluster? A few reasons. One, it's fun. It's really fun to play with these guys. Another one is I do like to, what I want to work is on pushing the limit of a machine. So if you do that on your local machine with virtual machines or Dockers, it will be a huge mess because everybody is fighting for the same resources. So doing it on real hardware or something like a cloud, it's way more useful. And as I want to push the limit of the hardware, Raspberry Pi is a really small hardware. You don't need to push much to get to the limit. So it's way more simple than if you to get a EC2 machine with a nice big 4 cores and 8 GB of memory and whatever. So the demo. I have 3 applications in my demo. I show only 2, in fact, on this slide. I have one application which is just a play application which gathers some data and some about the whole systems. I will show you just to know how the system is going. I have so the Reactive application. It's a Anstract application. I don't know if there is talk about Anstract in this conference, but Anstract is quite really nice if you want to process data in a streaming fashion. And you create a graph of how you want to analyze your data, and you get something which follows the Reactive manifesto, and so you can integrate in a Reactive application. So in my Reactive application, I have the first part, which is the random number generator, which I can tweak to say, I can say to the random number generator, I want to get, I don't know, 4,000 numbers per second, and the random number generator tries to give me that. And then I have so I can stream configuration to be able to do computation of pi using random numbers and slicing the random numbers in different ways to kind of see if I get different values of pi's and things like that. All the data, I kind of merge it and send it to Spark Streaming to do some analysis on it, mostly basically how good is the result and what are the differences and how fluctuating are the results depending on how I manage to calculate my pi value. So let's check that. Yeah, this screen just to show you that I have a Spark cluster with just two worker nodes. So on my 5 node clusters, I have one node which is kind of the gateway, which also running the Spark master. It doesn't really need much processing. And the workers are doing only Spark work because they need as much as they can. So I have my small play application. Oops. which just tell me the information about the random number generator, so I can change the value I ask. I can update the rate I want. I get some values of pi, so it's mostly to just see that my system is alive and that my computation of pi is pretty bad. And information about the Spark job I'm running. And that's the UI for Spark streaming itself. I can just refresh, which is, it's not a reactive UI. It doesn't refresh, it doesn't do anything. It's quite annoying. So on the top, I get just an input rate, how many messages I receive, which is normally 3 times the rate of the random number generator. Scheduling delay, which is something which will be interesting to see when we get in bad situation, and how long it takes to process. So in this configuration, I ask to run my job every second, and right now it takes 250 seconds on average to process the data. So I'm fine. I mean, it takes, so one more thing I need to say about Spark streaming, it gathers data, and in fact it doesn't run the job. It schedules a job to be run. It says, now that I have all the data, I want to run computation on this data. So processing time is fine and everything goes well. So let's try to push it a bit more. So let's go for 1,000 messages per second. So my rate automatically updates. It normally should stabilize at some point. I mean, it's the thing that measures the rate is totally independent of the thing that generates the value. So now sometimes the count on second is not quite aligned. And the number of records is still basically 3 times the same. Execution time went a bit higher. If we refresh, it was at like 250 before. And we get over 600 milliseconds. So we're still fine. We're still in less than 1 second. So let's double that. So rate updates, stabilize, and we are good. And we can see also that, I mean, I'm sending way more numbers. So as the computation is done with random, computation of pi is done with random numbers, the more numbers I send, the better pi I get. I mean, it's still not great. I have like 2 decimals, good. It's not really great. And execution time is still a bit below 1 second, so we're still fine. So let's double that again. Just, oh, okay, let me just check one thing. It's the wrong demo. Let's restart. The second demo. It's okay. Okay, just restart it. Need to. Because the difference is when we get to too much data. And I was running the wrong part of the demo. So yeah, so Aka streaming is basically right now waiting for Spark streaming to start to pick up and send data to it. So let's refresh. Okay, let's get back to 2,000 requests per 2,000 number per second. Okay, and yeah, so execution time is still under 1 second, so we are fine. And with a smaller timeline, we can see a bit more the variation of time, and you can see the number of elements getting in. So let's go to 4,000 elements per second. And my random number generator would be nice if it was not going too high. Okay, so it's hovering over 4,000. But we can see here that execution time is 1.5 seconds, basically. And this number that we didn't really look at before, it's at 3,500, and it's growing fast. And what does it mean? Okay, so we get back to the streaming UI, and you see that scheduling delay is growing fairly fast. So scheduling delay is at the end of the interval, you say, I want to compute my analysis on this data, but the previous analysis is not finished yet. So it's scheduled and to be run later. So in a few cycles, I'm getting to what, like 15 seconds? Yeah. So I'm trying to compute every second some data. I'm already like 15 seconds late on any data I get. And if I get it to run longer, it will just grow and never stop. So I will just make it stop a bit, in fact, so we can see later. And if I let it grow, we start to feel Spark has some memory where it keeps the data to be processed, and that starts to be filled up. And Spark is fine. Spark starts to cache this data on disk, which makes the whole system even slower, because you start to, in addition to just keeping the data in memory, you start to cache it on disk. So you get your processing, which is even lower, your scaling delay, which is even higher. And when you get out of this space or whatever, well, Spark doesn't crash, because Spark almost never crashes. It will stop processing. And you likely won't process, some data will likely be lost and not processed at some point. So let's see again. So I just changed, before my last piece of talk, I changed the random number generator to just pushing 10 message seconds, so almost nothing. And I'm still in the process of recovering from the delay I had before. I'm still processing the old data. I'm still not back in a way, yeah, so you can see that, yeah. So it took some time to go to the peak of the problem and then to recover at some point. So what can we do about that? Demo. Back pressure. So the way we get things work about managing too much volume in reactive applications, and specifically in application which are using ACA streaming, it's you use back pressure. Back pressure is a fairly simple idea. Is you have a consumer which start to get overloaded, and you just tell the producer, I cannot handle that much. Please send data slower. That's really just the basic idea. And the classic example, so if you ever looked at the TCP level API, every time there's a frame which is sent on TCP, at the TCP between each side, the side sending the frame tells the other side, this is how much buffer space I have. So this is really back pressure. And if you start to hammer too much a service that it cannot process fast enough the data incoming, and and the buffer gets full, then you get some interesting exception on your producer side that I need to look it up again, but it's something that it's not quite clear why it's not working anymore. So TCP does have back pressure. So the idea is we want to kind of use the same thing to be able to do, we want to do back pressure in the system to be able to not have the case when Spark is overwhelming by data. So correction in Spark. So a long time ago, in Spark line, meaning like 9 months, maybe a year, there was nothing really good to do conjunction support to do back pressure. You could just set a flight rate saying that I don't want more than so many messages per second, which is totally, it's not really great. If one of your nodes dies, your number might be too high because you cannot process fast enough. And if you just add more resources to the cluster saying that I want to do more, well, you can still not do more because you are limited yourself to so many messages per second. So 1.5, Lightbent, and with the help of Databricks, which is the commercial company behind Spark, we worked on added back pressure in Spark. So instead of having a static rate limit, we have a dynamic rate limit, which is estimated at every cycle, every interval. And this information is sent up the chain to the receiver, so the receiver can then tell its producer of data to please slow down. So the way we estimate the rates is fairly simple. Is every time there is an execution on a mini batch at each interval, we know how many elements were in the data, how long it took to execute the operation, and also if there was any scheduling delay. And from that, we can just do a simple division, and we get a number of elements per second that we can process every number of elements per second we can receive and process without any problem. But just doing this simple operation just tell us what is the theoretical limit. And sometimes things change, and maybe we do get some scheduling delay. At some point, the system, for some reason, slowed down a bit. Maybe one node died and was restarted. And so the whole system can always handle the right amount of elements, what we want. But at some point, it was slower. So it did accumulate some scheduling delay. So we need also to be able to manage those cases. So the way we manage that is to use, in fact, a proportional integrative derivative algorithm, a PID for short, which is able to manage the fact that sometimes the value you give to the value that the system is computing might not be quite the right one. I need to change slightly the value to manage additional parameters, initial problems. This algorithm is nothing new and just something reused. The most famous case that this algorithm is used is to manage cargo ships. Huge cargo ships, when you start to turn the wheel, at some point the ship will turn. But if you don't push the wheel back soon enough, it will overturn. So they use this type of algorithm to make sure that you get to the limit, you basically stay at the limit and never overshoot too much. So it's exactly what we wanted, to make sure that we are always at the limit of how much we can process, but never overshoot too much. So it's fairly simple to configure just two configuration information. And if we want to speak Kafka, we can speak Kafka after. Kafka is really great for fast data information. So this is a graph of running the same test case with a system without dynamic rate limit or with dynamic rate limit. So at the bottom is the amount of data that is been sent. So there is a spike of data which we send twice the amount of data, and it starts to be too much. So it takes too long to process, so we start to accumulate delay. In the case with the dynamic rate limiting, so it overshoots a bit, but it detects that it's overshooting, and there's some delay which is added, but it reduces the delay over time to get something which is stable. So it's almost all good, except that there's still some limitation of what we did. It's the computation. So the basic estimation is done on the assumption that execution is linear. For every record in your data, it takes the same time to process it, which is not always true. Sometimes some values maybe take more time, or your algorithm might be slightly exponential, so if you have more data, it takes more time to process. It is not a real problem, because PID will manage the case and give you to a stable value, but it's a bit like this example. This example, we do overshoot, even if we are able to compute correctly. It's because with this example, it's using not a too smart receiver that when it gets to the limit, it's slowed down a bit. So it's why we get this thing. So there's a few limitations which in practical are annoying but not breaking the system. So it's kind of something to know. So yeah, reactive streams. So I have a reactive application which is compatible, which follows the reactive manifesto, which has a full support for back pressure. I have Spark streaming, which I can enable back pressure in it. So now I need a way to connect the two together. And reactive stream is exactly that. So reactive stream is a really short it's a spec, a library, whatever, set of classes which are meant to connect two systems which have flow control, back pressure. So if I can just show you the web page, so that's reactivestream.com is the description of the page, and this is really the API of the interfaces that are defined. And in fact, there's only three interesting ones. The processor is just a combination of the two of those API, and in total, there's 7 methods to implement. So it's fairly simple to implement. But it allows, oops, where's my thing? But it allows you to connect systems that know the back pressure about flow control. Okay, let's go back to the demo, which I didn't correctly reset, which is, I'm not in, my timing for my demo is a bit weird. So let's restart everything and enable back pressure and the connection between Spark streaming and my application, and see how we work, how it does. To restart. Come on, faster, Spark. So yeah, as I said sometime when I do presentation for Spark, Spark is for big data. It sometimes takes time to do small things because it doesn't do small things, it does big data. So it takes time to start and stuff. So what was I configured to? So I was configured to send 10 messages per second, which is nothing. So let's get back to the 1000. And so yeah, so the number of elements grow. Processing time is whatever. Testing. It's a bit higher than before. No, it's fine. And we don't have scheduling delay because we don't have too much data. We get back to the 2000. And we should still be fine because it's still under the rate of the maximum we can handle. We are just under 1 second, but we are still fine. And so when I switch to 4000, so I switch to 4000, it goes to 4000, and in fact, the rate I see as a random number generator is around 2000, 2500. So this is really showing that the full chain from Spark streaming. So if I get back to the furthering, I should make a copy of it. So Spark streaming gets the data and it computes how much it can handle, and in this connection, it says how much data it can handle, which and this information is pushed all the way back to the random number generator, and the random number generator decides what to do because it cannot push enough information. So in my small demo, what I do is I just drop values. If there's too many values, I just drop values, which is something that in a real use case, it's something that is possible. If what you are doing is processing logs, and if in addition to, well, which is done most of the time in system like that, is you process the load as fast as you process the logs directly, and at the same time you store them for further analysis. So if you have a lot of logs, you may be able to just drop info logs and maybe even warning logs, because if you start to get too much data, what you still want to be able to process error logs. You still want to know if there is any problem. So it is one solution that if you detect that you cannot push data fast enough, you can just start to drop data if you know there's some data which is less important. Or another solution, which is working very well also, your application can just see, you will have to measure at different places, but if you measure more the rate of data you try to send and the rate of data you are able to send at this level, you can see, Spark streaming is not fast enough. What can I do? Can I just restart a new node? And then Spark streaming should be faster. Spark streaming is fairly linear scalable, so you're good with that. Okay, let's get back to the right slide. Yeah, so that's basically what I have. So if you have a Spark streaming application and you want to make sure that you are covered in most of the case, you can push up from Spark streaming the information that Spark streaming might not be fast enough to process your data, and then make smart decisions about what you can do in a specific case. Okay, thanks. We have a question, yeah.
So my question is, when you connect the reactive application to Spark,
yes.
Do you have any examples of how you do that, or are there some ready-made connectors? And
I'm using a homegrown because it was simpler for me, but there's implementation of Reactive Stream over TCP that exists, which is doing more than what I'm doing, which is allow you to send even multiple streams over the same TCP connection, and the back pressure information also over the connection. I don't remember what's the name, but if you go to the Reactive Stream project, you should be able to find information about it.
Okay.
Hello, I have a question here.
Oh, sorry, yeah.
How is back pressure implemented in Spark 2.0?
Well, Spark 2.0 still have Spark streaming,
Yeah.
so you can still use Spark streaming, but Spark streaming is using the old, the low-level RDD API, and Spark 2.0 is pushing more for the higher-level data frame dataset API. And on the data frame dataset API, there is a new streaming system which is called structured streaming, which right now has no idea of back pressure. So in 2.0, structured streaming will still be experimental and not even support a real stream of data. The only thing that you're able to support is the fact that it's looking at new elements, new information which is arriving in a folder. So processing new files that are landing in a folder. So I spoke with TD, the main implementer of structured streaming at Databricks, and right now they don't even have a clear view of what will be the API for a more custom receiver. So it's still something which is on flux, and there won't be any real answer before 2.1, before Spark 2.1.
Okay, thank you.
The standard, or what does it say in the definition of back pressure when you handle multiple consumers? Like, I got one consumer who is too slow, the other one is way fast enough, he can handle it, but you apply the back pressure up to the source?
Yeah, so you do apply the back pressure. By default, by simple implementation, you implement back pressure up to the source. And then, as I said, my thing is you may want to measure it somewhere lower in the chain, in the graph, and do your smart resolution of the fact that the system is too slow at the disjunction point. I just have the disjunction point.
Hi, thanks for the talk. I just wanted to check, is your source code open and available to...
I need to push it.
Okay.
It will be on Skyluc at GitHub,
Cool.
SKYLUC.
Okay, thank you.
Could you show the source code of the point where you're handing over the data from Akka Streams to Spark streaming? So this is the interface where you use the reactive interface, I think. Yeah.
Yeah. So okay. Let's see if I can. Where is this code? I think I have it on Bitbucket. I need to find my code again. There we go. Where is my code? Spark demos, right? Yeah, by parties. So there's, well, I can, yes. So what I have is, yeah. So Spark. So the way to create new receiver in Spark. Trying to make that bigger. The way to create a new receiver, a specific receiver in Spark, is to create a receiver in input streams, which is the basic API of custom receivers in Spark. So what I created is a receiver in Spark that when Spark asks it to connect to something, it creates it creates a subscriber. So in Reactive Stream, you have publisher and subscriber. The subscriber subscribes to the publisher. And what I do is I do have a publisher of data, which is my connection, my true TCP to the Reactive application, which is on different box. And I just create the link in the Java, in the JVM inside. I create the link between my receiver and the publisher, which is already connected to the endpoint of the Reactive application itself. And I mean, it's just so what I get on the where is it? Yeah. So what I get from Spark is updates of the number of messages per second I can receive. Spark says it can receive. And I have some custom code, which is a bit ugly, but I like to play with it, which transform this idea of request per second in something which makes sense in the Reactive Stream Reactive Stream API, because Reactive Stream API is just the subscriber tells the producer, I can now, at this point, I can receive 100 message, and then later I say, at this point, I can receive 100 more message, and things like that. So that's my connection between the two. And then I have Reactive Stream over TCP implementation, which connects on the Stream application side to make the connection between everything, and send the back pressure information over.
So does the Spark side, does it support SSL, TLS?
No, in fact, well, the SSL support TLS will be in the Reactive Stream implementation over TCP you use. The connection I do on Spark is really inside Spark, inside the receiver, which is run by Spark. And then, so basically I change Reactive Stream elements. So I have Reactive Stream, which is my reactive application, which is Reactive Stream component. I have a component which is Reactive Stream over TCP, which in my case is just really simple and just do over TCP. The more official one, I don't know if it supports TLS. And then I have the connection between this connector and Spark streaming itself.
Hello. How does back pressure works when the bottleneck is not the processing but the network?
It depends of what you use for as a transfer over the network. So I'm trying to think. So yeah, there's multiple cases. I don't know how well supported it is. In fact, it's a really good question. In my simple implementation, it might be a problem. So let me think. No, yeah. So in my simple implementation, it's not a problem because I start to ask for more elements when I received enough elements. So if the network is too slow and I don't receive enough elements, I don't ask for more. So I mean, the back pressure is always working like that. You receive some data, you have basically some buffer size you know you can use, and you ask for more elements. So in my implementation, yeah, it will basically I will not ask for more data because I haven't received all the data I can handle yet. But you might still get in trouble because if you start to fill up the TCP buffers, then your producer cannot push to the TCP. It will block. So the implementation of the Reactive Stream API over TCP need to be done correctly. Thanks everybody, and have a good afternoon.